Oh, there we go. Did everybody have a good spring break? No, I heard that in the back. Well, I know that a fair number of you, and actually good for you, a fair number of you devoted some portion of your spring break to native son, because as of this moment in time, in real time, this is Tuesday, over half of the class is finished with it. So congratulations. And I'm imagining that's a fair number of people who are actually here in the room. We've got a couple different things to do today, which actually makes it a pretty good day, but I better organize it here so I don't forget anything. We are still actually talking about project management. Remember how we went to Gantt charts before spring break and we skipped calculating risk, because that's kind of a module on the side. That is back on the agenda. Hey, Dave, I noticed that it's not the program out on the screen. Is there any? Oh, cool. Oh, thank you. Dave is doing us the favor of running the show today and actually for the next couple weeks, because I don't know if any of you have ever met Kevin Hartman, who's our actual technical director. He's out on paternity leave with his brand new baby daughter. So, congratulations. All right, now we have to get back to work. Sorry about that. That will finish up Chapter 7. We'll go on to Chapter 8, Location Planning. Just talk about some basics probably today. Although we're going to talk about a series of techniques for picking a location. We might start on one of them, cost volume analysis, which I think will seem pretty familiar to you from other classes, but nonetheless, right, I know a lot of people were, good for you, aiming for the 4 credit point deadline. Right now, you can still earn 2 extra credit points. Actually, why don't I switch this up for just a second, since a lot has happened over spring break. You know, this is our UB Learn site. There's the information about the extended office hours today. Oh, and I know you probably saw the messages that were pushed out from the posting of this, but yes, oh, by the way, it's never too early to start thinking about it, not stop thinking about it, right? After this week, next week, at the end of the week, we have exam 2, the super multiple choice. I posted them during spring break. And congratulations to James and Eugenia, our winners of our, you remember we had a forecasting contest? I know that seems like it was now a whole nother lifetime ago, before exam 1. If you'd like to see where you ranked, just click on that link right there and that will jump you over to the bulletin board, and I posted a spreadsheet that shows what the actual values are and what everybody's forecasts were, and you can find yourself there. You may be among the winners of, remember we had point prizes for, I think it was the first 30 places in each case. You should be able to actually see that in the grade book if, in fact, you won one of those prizes. Okay, so that was a quick catch-up on what's actually here on UB Learns. Oh, right. And related to this, I mean, before we get started back on the textbook stuff, I had another tab open here. This is the competition information page on our project website. Remember, we have 3 competitions going now, least days, least cost, and least cost with overhead. We have prize points for the top places and the first 30 places, and the last time before spring break, I showed you this. It was heavily populated by the United States Air Force Academy, right? Now you can see with all of that activity over spring break, yes, good job. We are occupying many more places on these leaderboards, although this is not over yet. Oh, right, and I just wanted to mention again, if you're just interested in the competition, you have through, in Buffalo, on the Buffalo calendar, you have through Friday, you know, all the way to midnight for an on-time submission just for grading for native son. That's the deadline. If you're interested in the competition, it says it at the top, it says it a couple other places. Remember that that deadline, like you've got a super short schedule, right? That deadline is at 5 p.m. It's set ahead of just the actual submission deadline. It's independent of it. You have to get that entry in by 5 p.m. All right? And any questions on that? And if your entry is in already, well, you may have already won. We'll see. Okay, then we had better go back to before spring break. We were working on a problem. I said, oh, this is a PERT problem. It's a lot like CPM, except it has this funny extra feature of you don't have exact information on how long tasks are going to take, but you use these formulas, and then it turns into a CPM problem, right? And as I walk over here to the screen, I keep walking past the blackboard where I recopied our scratch work for that problem, right? We worked it. The CPM, the whole middle part, 80% of it's the same thing as we did last time. Early start, early finish, late start, late finish. And we came to the conclusion, you have to check everybody that's attached to the finish line, but we came to the conclusion that this smaller problem we were working on was 27 weeks long, right? And then we went on and we drew a Gantt chart because then I wanted to talk about native son. So we skipped the part that the RAND group invented that tacks on the end of this technique about calculating risk, and that's why it's still got a separate name, PERT versus CPM. Let's go back to that. Because I had raised that question before spring break. I said, okay, this is, don't let me confuse you, the expected completion time of the project, 27 weeks. What was your confidence, in fact, if somebody asked us how long it was going to take, that it would be 27 weeks? And it turns out we weren't that confident of that. It went back to, this was our scratch work, but the reality of where we started, we had said, for instance, filming the scenes might take as long as 30 weeks, that one task alone. We knew it was a possibility, which means it's not a guarantee that we've done in 27 weeks. Right. Well, then, if somebody's asking us, because this is actually the context in which this was all invented, if somebody's asking us, they want an answer right now, what should we tell them? If we tell them 27 weeks, the probability that we'll actually be done in that amount of time is actually quite low for this particular set of data. Well, then what should we tell them? Well, this is the technique for testing how safe your answer is. For instance, I think at the bottom of that page, not this one, but the one where we did the scratch work, doesn't it say 29 weeks? Like, well, what if we told them 29 weeks? Is that safe enough? It's longer than 27. Okay, let's talk about how you test the safety of your answer. Now, to give you a frame for where the actual algorithm to come up with the answer for what's the risk of 29 weeks, we do have to back up to, and that's why I have the old sheet here in front of me. Where did this come from? This business here that gave us that number that we used in our calculations and got 27 weeks. Let me switch to a cleaner looking picture just to take you back to that conversation that was way before spring break. We don't need that website anymore. I posted some PowerPoint slides for today, and this I clipped right out of the book. I had sketched this on the board. It's just, it was my freehand sketching. It didn't look as good. This figure 7.8 in the book. This is, remember, the whole business about a beta distribution? Oh, right. It's meant to represent the uncertainty of each task time. And there's a whole lot more things that can go wrong than can go right. Right. It was the actual source of why do we ask 3 questions, because we're trying to spot 3 places and figure out what this shape is that represents our uncertainty. So yeah, I got that. That's where the formulas came from. Now, here's the theoretical model. Here's the argument all the way from when the RAND group first invented this for the Polaris missile project. A project, the whole project, is not done until you have successfully worked your way down all the paths. Does everybody hear that? We've been talking about the critical path, the longest path, the path that gives you the length of the project, but we said a path is any route from start to end. The project is not done until all the paths have been successfully navigated. Therefore, the chance that we will be done with the project has to do with the chance that we would actually squeak down all those paths within that amount of time. You say, yeah, okay. Now, here's the complication. We said at the beginning, oh, the length of a path, that's an easy concept. You just add up the durations along the path, right? Yeah, and that's the length of the path. The path ACE in this particular project that we're working on right now, this problem, is 27 weeks long if you add up A plus C plus E, because it's the critical path. Okay, ACE, or any other path, name off the tasks. The problem is we're adding up numbers that are wobbly now. And this is the wobble in each one of them. Well, when you add up a bunch of wobbly numbers, maybe it'll be this number, maybe it'll be that one, maybe it'll be this one. It doesn't matter how they're distributed originally. Does the phrase, the central limit theorem, bring back any memories from another class? If you have a string of things, right, and you're concerned with the outcome, like there's all these different tasks, and there's uncertainty with each of them, but we're stringing together and we're saying we don't really care about the individual tasks. Just tell me how long the sequence is going to take. That's all I want to know. Doesn't matter how the individual tasks are distributed. The theory is that the overall outcome will be normally distributed, basically. I'm playing a little fast and loose with but the way we use it in operations. The overall outcome will be, everybody hear that? Normally distributed. Not some weird lopsided thing, but a normal distribution. Oh, okay. So since I'm worried about, but notice this transition, because it's important to actually working one of these problems and getting it correct, I am suddenly transitioning away from being concerned about individual tasks, and I'm becoming obsessed with the paths. PERT, when you get into this calculating risk part, is obsessed with the paths through your network. You do all your calculations in terms of the paths. Now, one of the reasons why the problem that we were working on was relatively small is because I wanted a problem that didn't have like 20 paths through it. Because I did want to stop and actually look at what we were doing. Now, this is note page 68, and we're already looking at the idea of maybe padding our estimate by 2 weeks. By that we mean the problem we're working on, what's the risk associated with 29 weeks? Okay, you can see that the 3 paths are listed here. What we're going to do is not a mandatory step in the actual calculation of risk, but, oh man, I never can find something when I want it. Where's my straight edge? Aha, it was hiding from me. A straight edge. It is a visual explanation of why we're going to do the calculations that we do. There are 3 paths. Each one of them has a certain length. If you look, path AD is 26 weeks long. That's its expected length. Path ACE 27, we knew that. That was the critical path. And actually path BE is really, really short, right? 7 weeks. Now, I wanted the straight edge because I wanted to draw the deadline. The deadline, I just said it, well, what about 29 weeks? So, loosely speaking, right about there. It cuts across all of these. We're saying a project is not done until you're done with each one of the paths. Here's when you need to be done by. Here's what you're expecting each one of them to take. That looks pretty safe, except we know that there's going to be some wobble. Now, I want to draw the wobble. This is the expected value of path AD. I'm just going to do the one on top. We said, oh, but that's the result of these 2 things which are normally distributed. Actually, this one, I think D was fixed. But at any rate, this will be a normal distribution. I just don't know how big to draw it because I don't know, that's the mean. What's the variance in that path? Oh, yeah, actually I do know what the variance of that path is, although I have to remember a principle of PERT. The variance in a path is the sum of the variances along that path. Did everybody hear that? That's something that's just going to come up over and over again. You're like, What? That sure sounds like trivia. Well, think about it. The length of a path is the sum of the durations along the path. The length of a path is the sum of the lengths along that path, right? The variance in a path is the sum of the variances along that path. You say, what do you mean variances? Right. Why did we calculate those? Remember that at the beginning? We said, you know, we're not going to use this for a while, but let's go ahead and calculate it. Let's calculate the variance in each one of these tasks using that formula right there, you know, perfect formula sheet material. We're looking at path AD right now. Well, the variance in path A is 2.778 from our work before, and the variance in D is 0. It didn't vary. That's the variance in that path. 2.778 plus 0, that's the D, equals 2.778. All right, how big do I draw the normal distribution? Well, I need to do a little math in my, well, I can't do math in my head, but if I take the square root of this, right, and that would be the standard deviation, I know that most of the curve is within 3 standard deviations of its center, which means it basically looks like it's got to be centered on that, something like this. You can see I marked some for sketching. Here, ACE, the variance in this path is, I have to roll these up again, that same 2.778 plus for C, 11.111, plus for E, ACE, 1.778. I get a variance of 15.667. It's within 3 standard deviations, most of it, of its center. It looks a little lopsided. It's supposed to be centered on that, but that's basically what path ACE looks like. And then path AD, the variance is 1.89 if you add it up, which means that it's another small one right here. Why are we doing this? Because this is an illustration of what we're paranoid about. Do you see where the curve spills past the deadline? That's the risk. See how BE doesn't come any close? What that's telling us is that particular sequence, B, the soundtrack, and then E, the editing, that's not likely to cause us any problems as far as this promise of being done in 29 weeks. But ACE, it looks like there's a big problem, and you know, we're not even out of the woods with AD. Now this, we did this by hand, just want to triangulate. Much prettier picture in the book. It's not exactly the same problem that's being worked in the book, but it works out that it has 3 paths as well. And that's what this illustration is. It's just not on separate lines, right? There's these 3 paths. These are the distributions associated with each path, and this is what we're worried about right here. You say, all right, now how do we translate that into the risk of, if I answer this particular number as our deadline, that I'm actually going to be late or wrong? We have to do a little review on probability distributions and then the normal distribution. In red here, here's a nice one. This is the path. It's a pretty long path. This whole thing represents everything that could possibly happen with that particular path, just like the ones that we drew. That's what the whole represents. Everything that could possibly happen, and the height of the curve over a particular number is the specific chance of that happening. That's the theory. What we're concerned with is not the whole. We're concerned with the part that's being, the way I think about it, amputated by the deadline, because we want it to be done by the deadline, and these are all outcomes in which it's not done by the deadline. And you are not done with the project until you are done with each and every path. Oh, well, since the whole area of the curve is everything that could possibly happen, and the stuff to the right of that line is the stuff that I'm worried about, then the proportion that's been amputated is the risk that that's actually going to happen this is the theory, the first and only time I ever do this, right? These are all the possible outcomes. I'm really hoping it's not one of these over here. If I figure out how many of them are over there and what the chance is, that's the chance I'll be embarrassed. So what I really want to know is just the area of the curve, right? The portion of it that got chopped off. So if I had some way, like some table that told me the area of the curve that is to the right of wherever this particular deadline was set, given that particular normal distribution of which you see the data there, you know, for that particular problem, then I'd be grinning because I would just look for it. But we don't have any such thing. We don't. But we have very easy access, and it's at the back of virtually any business analysis textbook that was ever written. We have information on the area of the curve that is amputated by a particular value, given that the curve happens to have a mean of 0 and a variance of 1, which is a very specific normal distribution that's not pictured here, and it's not a feature of the PERT problem we're working on either. But it has a name because it's famous. A normal curve that has specifically a mean of 0 and a variance of 1, it's a famous normal curve. It has its own name. Anybody remember that? It's also a keyword. Yeah. Well, the bell curve actually could be any normal curve, or often called bell curves. One that specifically is right over 0, centered on 0, and has a variance of 1. It's your standard normal curve. Your standard normal curve, and you can tap into it to quickly calculate these values because you can change any curve into a standard normal curve. That's why it's famous. You can translate any curve, no matter how exotic its numbers are, right? Because these two numbers describe the curve. You can translate it very quickly into a standard normal curve. And the little formula, little tool that you use to do that, you've had before. Is that bringing back any memories? It's called the z-value. Okay, now, this was all motivating why we do what we do when we calculate the risk associated with a deadline using the PERT methodology. Stop. Now we'll just talk about literally the steps. Well, what is it that I'm supposed to do? Well, remember, you don't actually have to sketch like you see in the picture. That's not a mandatory step. You don't have to sketch those curves. You probably do want to, especially if you've got more than 1 or 2 paths, have some sort of table, because this is what you do. First off, you need to list off every path through your network. We're obsessed with paths. The risks are associated with the paths. You then need to note the 26, the 27, and the 7, the path mean. That's the center, right, of the curve. And you need the path variance. We calculated that on the page before. I'm just copying those numbers over. Why? Because you want to calculate a z-score. Now, from like MGQ201, MGQ301, the kind of the generic statement of the so-called z-score is it is the number that you're interested in minus your particular curve's mean, that's that part, divided by your particular curve's standard deviation. And this is, even if you know a lot about this, a common source of error. Be careful. We calculated the path variances. The variance in a path is the sum of the variances along the path. What you need for the z-score is the standard deviation, which is just the square root of that. You just have to remember to take the square root. Oh, now, this is the generic form of it. It actually has, you could write this again in terms of what we're doing. X, the number we're interested in, is the deadline. That's what we're sweating, right? Is 29 safe enough? Minus, I just labeled it, the mu is the path mean. basically the path length from our standpoint, and then that sigma is the path standard deviation. So, for instance, in the case of this one right here, which I said, you know, I think we're a little paranoid about that because it does seem like it's reaching past the deadline somewhat. What we would do is say, all right, the deadline is 29. That's what I'm concerned about, minus the 26. That's where that is centered, divided by the careful square root of the variance, 2.778. Now, I wrote all over this, right? You do this on your calculator, I get 1.80. I'm rounding to 2 decimal places for a reason. There's not really any point in going any further. 1.80. Now, why don't we just fill out this column? If you say for path ACE 29, it would be the same 29 minus 27, because that would be the path mean, divided by the square root of 15.667. I get 0.51. You can check me on that. And down here, if I say 29 minus 7 divided by the square root of this, I get 16.01. Now, rule of thumb, if you get a number bigger than 3, area from table, probability associated with path, forget about it, 100%. Huh? What? No. We'll fill in the other ones. They're a little more complicated. But remember BE on the page before? That's the little one that's not anywhere near the deadline. Okay, I'm saying that whole business about drawing the normal curves to scale, you know, that's actually not a thing. You don't have to do that. What you see, though, is if you get a great big z-score, that's what you have. You have a path that's not anywhere near the deadline. Don't worry about it. 100% probability of being done by the deadline. This is what we're looking for here, filling out that column. What is the probability we'd actually be done by 29 weeks if we tell the investors we'll be done by 29 weeks? Well, concerning this sequence right here, don't worry about it. Easy. Generally, in operations, if it comes out any higher than 3, we say, you know what, that's safe enough. Just probability of 100%, probability of 1. Now, here, this didn't pass. This is 1.80, right? That didn't pass my rule of thumb, and this didn't pass my rule of thumb at all. We need to figure out, wait a minute, what does it mean, area from the table? We calculated a z-score. Why? Because we want to use the z-table to figure out how much of the curve got amputated by the deadline. Z-tables, and actually this underlying assumption that everything that we're uncertain about is in fact actually normally distributed, which in modern times isn't necessarily always the case. There's a z-table right there. This is the back of the book. Do you guys remember how to use a z-table? You calculate a z-score. Basically, it's what you took your own curve and you translated it into this one. Now, here's the nice thing about z-tables, any textbook anywhere. They'll always have a cartoon at the top that tells you exactly what they're reporting. So what this is indicating is you look up your z-score and it's giving you the area to the left. That's the probability of safety. In our case, the amputation is what's left. Now, I said, well, that first one is 1.8. You look up the first 2 numbers as your row, and you look up the third number as the column. So 1.8, the first 2 numbers, 0. I'm looking right here, and I'm seeing 0.9641 right there, 0.9641. 0.9641. I have to remember that 0.9641 came from the table. Looked up that number right there. What's that mean? It means there's a 96% chance. Or if you're feeling really scientific, there's a 96.41% chance that you'll be done with that sequence within 29 weeks. Oh, well, that seems pretty safe. Let's look up the other one. 0.51, right? 0.51, 0.51. I'm looking at 0.695. 0.695, I have to remember that number. 0.695. There's only a 69 to 70% chance, though, that we would navigate the critical path in that amount of time. Okay, now, this is essentially the risks right here. Remember, the only thing we're trying to figure out is if we tell the investors that number, are we safe? How safe are we? These are essentially our risks. To finish this up, to roll this up into one answer, we need one other principle that's from MGQ201 and MGQ301. We're not done with the project until we're done with the paths, right? Okay, the risk that we'll be done with the project is the joint probability that we will be done with each and every path. They all have to pay off, right? We have to get through each of them. How do you calculate joint probability? You've got several different risks. They all have to pay off. You multiply them times each other. So that is the joint probability of every path. So that is this one, 0.9641, basically using your calculator, right? Times, I'm going to use an asterisk, this one, 0.695, times 100%, that's a probability of 1. I get on my calculator 0.67005, or basically 67%. And drop the mic. That's the PERT risk module. I just picked that out of the air. Is that safe enough? The answer is, well, there's a 67% chance, basically 2 chances out of 3, that you would actually be done. Is that safe enough? This doesn't sound very safe, right? Actually, that wasn't a fair question. Because you don't have any information about, like, well, what happens to us if we overrun the deadline, right? Or we get spanked, or what? You would need to know. Now, actually, in large-scale projects where people have invested in them, very often there are financial penalties week by week by week for overrunning the deadline, you know, and you'd have to start thinking about that. But right now, at least what we can say is that, well, if we tell them 29 weeks, 67% chance. If you don't like that chance, you better tell them something longer. Well, I don't know. What about 30 weeks? Is 30 weeks safe enough? Repeat these calculations. Put a 30 in for the deadline, for the x in the z-value, right? The number that you get all the way down at the bottom. I don't know. Do you like that number? And then that's how you assess the risk. Okay, so this is the extra part that's on the end of PERT that DuPont didn't invent for CPM. Any questions on that? All right, well, I don't know. Since we weren't told anything about penalties, I'm going to leave this here at 67%. Remember, a couple things. Notice PERT is obsessed with paths. You draw your network, you do all your calculations, and then all of a sudden everything goes to just being about the paths. Other thing, before I leave, I know I said it before, remember, when you're calculating the z-score, that's the standard deviation that's in the denominator. That's the square root of the variance. Remember to take the square root. Oh, sometimes people say, well, wait a minute. Why did we bother to calculate the variance in each one of the tasks and then have to add them up to get the variance? Because isn't it something like p minus o divided by 6 squared? Why can't I just calculate the standard deviation in each task? The standard deviation is always the square root of the variance. Because wouldn't that be simpler for me? I just go p minus o divided by 6. And you're right. That's the standard deviation in each one of the tasks. You cannot add standard deviations. You get the wrong answer. You can only add variances. This is a principle of probability distributions. You have to add the variances. You have to get the variance in the path. Then you take the square root. There's no shortcuts. So, just saying. Okay. Actually, I think there's an old exam problem that features that. There was us. Drawing that. So, what are the answers here? There's the answers. This is a CPM problem. You can tell because it just tells you the duration. There's something about a Gantt chart there. And this is actually a PERT problem, all in one inside of one paragraph. So those are good practice. Actually, before we go any further, sorry about this, Dave, I noticed that the slides were still up. Everybody saw the workings on the z-values, right? That stuff? When I was doing that? Everybody else? Okay, good. I'm sorry, just checking. I just wanted to make sure that that other image wasn't hanging while we were talking about this. Okay, this is something it does pay to practice. I'm just saying. Because we're all queued up to Chapter 8. All right. Done with project management for a while. This is, let me think, yes, we're making a transition from the strategic level down to the tactical level. This is one of our, it's probably the last overall subject in this class that's pretty much purely strategic, long-term decision. And that's the idea of picking a location for your operation. Remember from the very first part of class, how do you tell a strategic decision from a tactical decision? Generally, the strategic decision, once you make the decision, you live with it for a long time. Like, I want to go into business. Where should I locate? Oh, now, and this is the graphic that's in the skeleton notes. And it's implying that, here's another way to look at it. Look at a business and look at where it's at. Here's the argument. Where it wound up being was a struggle between essentially three groups of factors that were literally determining where the operation should be. It says regional factors, costs associated with inputs, regional costs associated. Now that right there sounds familiar versus site-related factors down here. There's actually a prettier version of this in the book because it's true. You know, this goes back to the first week of class. Remember the input-output model? We said you could take any operation and you could basically explain it this way. It is something that's taking in inputs and is creating outputs of at least in some total greater value. Well, this whole business about where should the operation be, it's basically couched in that argument. Because we say, all right, well, there are these factors that pull on it that are related to the inputs. There are these factors that pull on the best place to put your facility related to the outputs. And then that business about site-related factors, also known as indigenous factors, they're factors that are related specifically to the plot of land that you're looking at. Not like what you do, inputs versus outputs, but the actual piece of real estate that you're looking at. That is actually grounded in, if you think about, you know, this is the transformation process in the original input-output model. It's actually what we're talking about, is where, in terms of real estate, do you want to put it? All right. Now, this can be quite significant, but you have to go on a case-by-case basis. For instance, there are people that argue that, like here in Western New York, a lot can be explained of what businesses are here versus aren't here is related to the tax structure. I don't know if you read about like that in the, yeah. Okay, that's a good example of something that's indigenous. It's specific to the real estate. Most, though, major facilities, if you look at like, why is that? Why is, well, no, UB doesn't work. Why is the North Campus where the North Campus actually is? That's a lot of that is indigenous factors. Most other things, though, if you look, it's got to do with the other two. Now, there's an example here down below in the actual course pack. Oranges for orange juice and potatoes for potato chips are both grown in South Central Florida. Minute Maid has built its orange juice plants in South Central Florida, but Frito-Lay has scattered its potato chips all over the United States. Why? Okay, now, that is a little case study from my own personal experience, because when I was your age, I went to school in Florida. I went to school in North Florida at the University of Florida. No, this is not on the exam. But I also didn't have a lot of money. So I actually lived in a very nice house that was against the railroad tracks, literally, when you looked out the kitchen window. So one thing that I was constantly reminded of about 3 times a day, does anybody know what CSX is? Sometimes they recruit here on campus. CSX was the rail provider that used the railroad track, right? Hauling predominantly freight. At least 3 times a day, depending on what the schedule was and what the day of the week was, trains would go by the kitchen window, like if you were sitting at the sink, right? The house would start to shake, it's very loud, and a train would go by the kitchen window. So you'd be at the sink, and you'd be looking out the window, and you would see Minute Maid, Minute Maid, Minute Maid, Minute Maid flash by. Because what you're looking at is the big tanker cars of orange juice. They paint them in the same livery. There's an interesting term. It's not in the book, but a livery refers to how companies mark their assets, like the painting scheme on planes. With the livery for Minute Maid, they would paint the tanker cars to look like the cans of Minute Maid juice. So go Minute Maid, Minute Maid, Minute. Except then the sequence would go Minute Maid, Minute Maid, Frito-Lay, Frito-Lay, Frito-Lay. You would see the big Frito-Lay logo. That's the livery on their box cars. Their box cars did not have potato chips in them, though. Their box cars had whole potatoes. That's what was going by. The only other thing to complete this scene is it would go Minute Maid, Minute Maid, Minute Maid, liquid sulfur, what? Liquid sulfur. Minute Maid, Minute Maid, Minute Maid, Frito-Lay, 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 liquid sulfur, danger, toxic, liquid sulfur, Minute Maid, Minute Maid. Do you know that they transport liquid sulfur in the exact same tanker cars that they transport orange juice? Or it doesn't. It just says danger, toxic, liquid sulfur, liquid sulfur. Liquid sulfur is also produced in South Central Florida, and it was being brought up across here. I know that they would never ever mix up those tanker cars, right? But to this day, I have not forgotten that fact. Every time I look at Minute Maid, like in the supermarket. Now you say, all right, well, fine. You know, so here's a story, right, from like when you were in school. What's this got to do with like that business up there and like what I'm supposed to remember about location planning? Well, let's think about this. Think about this. Now you've got a little bit of room down here. Think about this in terms of the input-output model. Because I chose this story in that you have 2 products that are very, very similar. And if we were drawing the input-output model, here's the inputs, for instance, for Minute Maid. Right? Obviously, oranges, right? Here's the inputs for potato chips. Frito-Lay, Frito-Lay, Frito-Lay. Potatoes. You have 2 products that are very, very similar. You have 2 outputs that are very, very similar. Orange juice and potato chips. You have 2 very, very different decisions for the facilities that create these 2 products. One is very, very close to the inputs. It's down there in the groves, the orange juice plants. And one, the raw material is having to be shipped a great distance because the potato chip plants are not down there in the potato fields. They are scattered all over the United States. Now, I had made a statement, right? That's the transformation process. That's the transformation process. I had made a statement, oh, these are two very, very similar products. The reason I picked this, and yet there's such a vastly different choice for the location of the facility, which is the subject we're talking about right now, right? Okay, let me support the statement that these are two extremely similar products. First off, Minute Maid. Minute Maid is a brand name. Anybody know who that's owned by? Who owns Minute Maid? Coca-Cola. Yeah, that's its actual parent company. Minute Maid is a globally known brand name, right? This is just, I got stuff of Wikipedia. Minute Maid around the world. It's a food. It's relatively inexpensive. Same thing with the potato chips. Frito-Lay, Lay's potato chips. Okay, known around the world, although in the UK, you guys are in London, yeah, I know, they use the name Walkers, although it's still owned by Frito-Lay, who's owned by, this is interesting. Who's Frito-Lay associated with? Yeah, Coca-Cola's big rival, Pepsi. Okay, so interesting. So two global brand names that are actually branches of even larger companies. Both of them, that's on the output side. They're both foods. They're both distributed through the same outlets. Go to the input side. This is the input side, obviously, of an orange juice plant. They're both made from a single crop that's being brought in at high volume. There are all the oranges going by. I thought this was an interesting picture taken across the street on a phone. See the Frito-Lay logo? I know it's a little blurred here. These are the potatoes going into the plant. That is not a rail car. Actually, if you look very closely, that is a 60-foot tractor trailer. Do you notice how they're handling it? They're emptying it like it's a box. They're just emptying the whole thing to dump the potatoes into the input side of the potato chip plant. That is our early hints of, even though on the input side, both start with one crop, right? Both wind up being a foodstuff that you buy through the same outlets that is globally branded. Two big rivals, but a lot of similarities there. This is our hint, though, of what's different about the two, that they made such a different decision on this one thing, and that's location planning, where to put the plant. In the case of potatoes versus potato chips, when you buy the end product here, what is it that you've mostly bought? Air. Everybody notice that? That's another thing that is different about these two products. Somebody even did a graphic, and I just did a Google search and stole it, right? They apparently did an audit. And when you buy a bag of Lay's potato chips, you're actually purchasing, because the bag is puffed in terms by volume, 86% air, only 14% of it is the actual product. Versus you buy any form of Minute Maid juice, and you're getting a much higher ratio here of the, I mean, just for the volume. You say, well, yeah, duh. Oh, right. And why is that? Why is it that Frito-Lay doesn't have one big potato chip plant down there in South Central Florida, which is where they grow ugly but tasty potatoes, which is where you get a lot of your snack food from? Because when you see a Frito-Lay truck go down the thruway, the highway, if in fact it's carrying potato chips, we hope it's not going very far, because it's actually mostly, the truck is full of air, right? We said, you know, most facilities, if you look, why did they wind up where they are? It's the tension of inputs versus outputs. And that's the key difference of who won the tug-of-war here versus who won the tug-of-war here. With the potato chips, they don't want to ship them great distances, Because they're mostly shipping air. They're mostly shipping air, and why are they mostly shipping air? Because this is a very fragile product, right? And that's why they puff the bags full of air. Oh, which is why they would prefer the plants to be closer to where you're actually going to be eating the potato chips. Also, if you think about it, nice coincidence, think of the two crops. I said, oh, they're so similar. They're grown in same sandy soil, right? One's a fruit, one's, I guess a potato's a vegetable, or tuber. Well, technically, right? They're both a fruit or vegetable. Except, wait a minute. One of these two items, if you're talking about lots of them, like we were looking at, great truckloads full of them, one of these two is full of water. One of these two can crush and spoil, has a very high sugar content, right? It's the oranges. Yeah, actually oranges are much harder to handle. Once, actually not far from where I used to live, you know, sorry, another story, CSX put a actual boxcar of oranges. It wasn't headed. It was oranges to be eaten. They were being shipped on a sideline and lost track of it. And it stayed there 2 or 3 weeks. And they had to call out the fire department because because several thousand pounds of oranges had started to spoil. And because they have very high sugar content. So anyway, the oranges, you want to convert them as fast as possible into something that's a little more stable. Right? Yes. So you see the tension there, dragging the plant closer to the grove. So we can just dump the oranges. Whereas potatoes, especially ugly potatoes, are going to get cut up into other things. Right? You saw them shaking the whole truck. They're not worried about marring the potatoes. No, potatoes ship nicely. They stack and they don't crush. And the thing is that the end product doesn't ship. And so it won the tug of war. So it's this tug of war between inputs and outputs. Once it's true, and I'm cheating a little bit with my story, once they convert the oranges to orange juice, I wasn't actually looking at the final consumer product going by the window, right? I was looking at a tanker car of orange juice concentrate, which it's true, it was headed to bottling plants. If you remember, like from the Aquafina example, all over the United States. But the basic product had been made. And that was what was going by the window. That was orange juice concentrate. If you wanted to pop the hatch on the top of that giant tanker car and scoop some out and mix it with water, that's what you would have. You would have orange juice. All right. Now, that said, this still doesn't give you a means for, like, your own business to pick a location. There are a series of techniques for suggesting locations. Why is there a series? I mean, why isn't there just like one technique that we can talk about and be done with it? It has to do with the fact of the different situations, whether the inputs are important, like more important, whether the outputs are a little fiercer. They're the ones that are really pulling, and it explains most of why you're worried about where to locate. Or, in fact, it's more complicated than that. There's indigenous factors and there's stuff going on all over the place. What should you do? So, when we look at each of we'll look at three techniques for picking a location. Let's pay particular attention to the technique that we're looking at, like when would you want to actually use it. The first one coming up is cost-volume analysis. This, it says, technique for locating a production facility is generally if it's sort of the Minute Maid example and it's the input side that's doing most of the pulling. Oh, okay. Well, now wait. Facility has fixed costs that do not vary with output level, has linear variable costs, and only makes one product. We're saying this that we're going to talk about, like picking a location. This is a checklist, like if you were consulting, you would want to make sure that these things are basically true. Oh, you know, these two, well, this first one is really not a worry. Most facilities do have, but, you know, we should kind of review that. You've had it in other classes. Most facilities do have fixed costs, right? Fixed costs are bills that you pay regardless of whether you did anything or not. And the best way to remember their nature is to think about you have fixed costs yourself personally. It's kind of a micro example of that. Because, for instance, you had a location planning problem that you were confronted with when you decided to go to UB. You had to pick a place to live, right? Perhaps you rented an apartment. Notice that when you rent the apartments, it doesn't matter whether you're actually there or not. You still have to pay. Most facilities, the major source of their fixed cost is the equivalent of your rent. It's the cost of the property. It doesn't matter whether they use the facility or not, or how heavily they use it. They still have to pay the rent or the mortgage. And that's what we're talking about. We just want to identify that, right? Oh, we want to identify that at each of our candidate locations. Other fixed costs might be like, for instance, salary level. They say, oh, more companies should come to Western New York because our cost of living is lower, and so the salary levels are lower than in other places. But, you know, that's usually only a fraction compared to the costs associated with property. Facility must have linear variable costs. Yeah, this technique that we're going to go through kind of falls apart if the facility doesn't have linear variable costs. Now, what's that look like? That just means that it's generally simple multiplication. If you want to produce twice as much at the facility, it should cost you twice as much to get that production done. Well, that sort of makes sense. Yeah, okay, it's generally not that limiting, although there is an important violation of linearity that is associated with labor costs. And so we should note that. And so, well, wait a minute. An important association of linearity associated with labor costs. Yes. Normally, if you're paying somebody by the hour, you pay them a certain amount each hour, and it's simple multiplication, whether they work 2 hours or 5 hours or 10 hours, if they're hired as hourly labor. But in the United States, it's the Taft-Hartley Act, if anybody has taken business law yet. What violates the linearity once a person has worked 40 hours? You pay them overtime. Is it time and a half at a minimum? Yeah, it's usually time and a half. That's what we mean by linear versus nonlinear. That's what's known as a nonlinearity. Then if you're doing the scratch work about how much to make their paycheck out for, it's not simple multiplication because it's so many hours at the regular time and then it's so many hours at time and a half. Okay. You say, oh, so this can't be used for any facility where anybody might work overtime. No, not really. But it's just stop and think about it. Is this a facility like this very, very seasonal? And there might be loads of overtime. That's like a big deal. Then you might want to hesitate using something. The rest of this is quite simple, you'll notice. I'm just saying don't enter into it. Or at least don't buy the property yet if, in fact, there's going to be a lot of that. The facility only makes one product. That's not as limiting as it sounds. The facility can actually make a wide variety of products, and most of them do, or provide a wide variety of services, as long as you have one logical way of aggregating that. You know, in a little while, a couple of weeks, we'll talk about aggregate planning, and it'll be the same thing. Yeah, I know we do a lot of different things, but we're finding one way to roll that up into a single expression of activity level. Many, for instance, oil refineries will make many different grades of fuel, but it's very easy to aggregate that the activity into barrels processed. Fine. Call that one product. So that's not as limiting as it sounds. Now, the way the cost versus volume, the full name, analysis works is it's actually just easiest to just do one. But notice you always begin with a set of candidate locations. That's what I've been standing in front of this whole time. You begin with somebody's already done work and they've looked at sites. And they say, you know what? It looks like what we're trying to pick between is, and you know, practically speaking, if you're working a cost volume analysis problem, this data has to be there. It looks like we're down to Charlotte, Boston, or Omaha. Okay. They've picked candidate sites, and they've already gone and gotten those 2 readings that we've been talking about under the requirements. What's the fixed cost at the site? Generally got a lot to do with the property. And what's the variable cost for this 1 unit of production? So, like this particular problem, you can see that Boston has the highest fixed costs, and that would make sense because Boston is one of the most expensive cities in the United States for property. Although it's got the lowest variable costs, meaning the direct costs that we pay for producing or doing whatever that we do for value is the lowest in Boston. That might have something to do with the fact that it's a port and the other two aren't. Charlotte's the youngest city, lowest fixed costs and highest variable costs. All right, we just need to pick one of these. All of this technique is just picking from this list that has to already have been created. And in doing that, there is, you can see an easy case and then a not as easy case, but still pretty easy case. The easy case is if somebody tells you exactly how much you're going to be producing. Remember, you're trying to locate something like a factory, you're trying to locate a facility. It's the easy case if there's somebody who knows what the activity level will be at the facility. And it's being suggested here that it's 36,000 units annually, meaning whatever this is, that's what, once you build it, that's what it'll be producing, 36,000 units annually. Then it's just what I think of as a beauty contest. We just need to take that information and we just need to cost out each of the locations. Logically, the one that's the least costly will be our winner. So let me do the scratch work for that. Okay, one at a time. Charlotte. Charlotte, the cost of locating in Charlotte. Well, we'll pay $10,000 a month regardless of what we do in Charlotte, plus fixed cost plus variable cost. We'll pay $10 for every unit that we do actually produce in Charlotte. We want to multiply that by what? I want to multiply that by the activity level, right? So what number do I write here? I'm just costing each one of them out. I'm glad you said 36,000. Don't write 36,000. But I'm glad that you said it. This is actually really simple, so I'm deliberately trying to draw out the one thing that could possibly go wrong and you could get it wrong. When I wrote the 10,000, I committed us to calculating how much it would be to locate in Charlotte each month, right? Because each month you'd pay 10,000. 10,000, that's the fixed cost. Here's the variable cost. 10 times, I need to know how much we would be producing each month, right? What's the monthly cost of being in Charlotte, North Carolina? If we're going to be producing 36,000 annually, then logically, what would we be producing each month? 36,000 divided by 12 months of the year. Yeah, 3,000 is what we'd want. That's the number that you'd use. It came from this number, but it was divided by 12. I could have written 36,000 here. I would be calculating the annual cost of being in Charlotte. I could not write 10,000 here. I'd have to write 10,000 times 12, right? Because that we would pay the 10,000 12 times. Whatever you do, just don't mix up these two things, right? It's the only thing that can go wrong here. Because having straightened that out, now we know that it's 40,000 a month to locate in Charlotte. We just repeat that logic for the other two. Boston. Okay, Boston has the heavy rent, 30,000 every month, but the break on variable cost, that 2 times, it's the same activity level. Already I know I would prefer Boston to Charlotte because it's coming out less expensive, right? 36,000. I'm not done until I've tested all the candidates. Omaha. Omaha's kind of middle of North America and middle of the road here in this problem. 20,000 for monthly fixed cost, middle variable cost 5 times that same 3,000 because that is going to be the activity level. I get 35,000. We are done. What is the answer to this problem? Do all that scratch work. This problem has an answer. What's the answer to this problem? Omaha. Locate in Omaha. It would be the least expensive. Okay, now here's the thing. This is fairly rare for this type of analysis. It is fairly rare for somebody to know exactly how much you're going to be producing. Because let's think about this. We haven't even bought the property yet, let alone built the facility, let alone produced any product to see how it's selling in the market. I mean, we are years ahead, and we're generally not that confident. Okay, that's the not so easy case. Oh, and it's a graphical argument. All right, back up. Same information, but nobody will commit to the production level. The argument is, here's the best thing that you could do. Draw a picture of your situation. Now, you've got this blank graph. Helps to put some scale to it. The thing that we're not sure about is how much we'll be producing. So I want that to be the x-axis to represent everything that could possibly happen. From we open up a factory and we don't produce anything, right, starting at 0. A good scale here, in my notes, I counted every 5 grid squares and I let that be 1,000. Like here's producing 1,000 a month, here's producing 2,000. There's the 3,000 that we just looked into specifically, then 4, then more, 5, we can quit there. And of course, how are we picking? It's all based, it's an economical argument, economics. There. It's all based on money, right? Specifically monthly cost. So given that we're a little unsure here, we need a scale to represent what we're unsure about here. And a good scale is to count every 5 grid squares and make that an increment of 10,000. Like this would represent it costing 10,000 a month versus it costing 20,000 a month versus it costing 30 versus it costing 40 versus it costing 50. We don't need to go any further. What I'm going to do is simply illustrate what I'm not certain about. Oh, I could locate in any one of 3 cities. I'm going to represent each and every one of them in my illustration. For instance, Charlotte. I'm just picking the top of the list. Here's the deal. If I locate in Charlotte, North Carolina, and I'm just saying if it turns out that we don't produce anything, that's what happens. How much do I still pay every month? What is the monthly cost in Charlotte if, in fact, for some reason, I don't even use the plant? 10,000. That's that fixed cost. That's a point on this graph that's true about Charlotte, right? Now, I could pick any other point, right? I could calculate the cost in Charlotte and I could plot it that same way. Yeah, and then I'd have another point. Then I could remember that we said that this relies on linear variable costs, which means that when you plot every possible cost in Charlotte, North Carolina, the dots are going to line up in a straight line. Oh, well, if all we're looking for is a straight line, the only thing we need is 2 points, right? Connect the 2 points and you have the line. Oh, right, so I could pick any other point here. I could calculate the cost in Charlotte, North Carolina, mark that point, and strike it. And that would be every possible thing that could happen in Charlotte, North Carolina. And actually, I don't need to, because what's handy is we already did that for 3,000, right? We know that if you locate in Charlotte, North Carolina, and you produce 3,000 a month, that it costs you 40,000 a month. 3,000 was this one right here. 40,000 is right there. This dot represents that particular scenario. If you have found 2 points, you have found the straight line. This is every possible cost monthly we might incur in, label it immediately before you forget which one is which, Charlotte, North Carolina. That's literally every possible thing that could happen in Charlotte, North Carolina, and how much we would pay. Now, it by itself doesn't really tell you anything, because we might not locate in Charlotte, we might locate in Boston. Let's just repeat that process. Boston. If, it's my favorite point, if we locate in Boston and we don't produce anything, It's easy to figure out what the monthly cost would be. It's just the fixed cost, that's $30,000. Then I just need one other point, and we happen to have already calculated it. At $3,000, the total monthly cost in Boston is $36,000. Just got to make sure I mark this carefully. $36,000 is right there. Oh, so this is a lot flatter line. That's what low variable costs look like. They create a much flatter line. And then, just because we're on a roll, let's just go ahead and add Omaha. If I locate in Omaha and don't produce anything, the cost is $20,000. What was it at 3,000? 5? Oh, so it'll be right below this. Right there. So it's kind of neither steep nor flat. Middle of the road. That's Omaha. Okay, this is your vision in how to pick one of these three cities. And this is cost versus volume analysis. Now, how is this that you just created supposed to be an answer to anything? Now that you've finished it, all the cities on the list or whatever the locations were, they're all on the graph. We're not interested in the whole thing. We're just interested, starting from 0 and going out as far as you want to go, who is the lowest line in each case. Matter of fact, I would take a highlighter pen, start here with Charlotte. Charlotte is the lowest, meaning you would prefer Charlotte. It's the lowest cost. That's what the graph means. Up to, now you notice this, a certain point. And then it stops being, and that's why we needed the graph, because it's showing us where these things switch. Then there's this flat spot in here. That's Omaha. Oh, and that makes sense, because that's right over the 3,000, and that was our answer from the easy case? Yeah. But, you know, you wouldn't necessarily, if you're thinking of higher and higher production levels, you wouldn't necessarily want to stay in Omaha because it doesn't stay the least expensive forever if you're thinking about different levels of monthly volume. Boston, basically you pay off the high fixed costs and that low variable cost starts to pay off. Okay, so just a little bit of management science trivia. If you're interested in business analytics, we have a term for this. We call this the efficient frontier. By that I mean that shape that you then basically retrieve or harvest from this graph. All right, it's got some turns in it. It's the lowest line in each case. So, all right. It still doesn't answer the question. Do I want to be in Charlotte? Do I want to be in Omaha? Do I want to be in Boston? My problem was, and the reason that we got to this point, was that I didn't know what the monthly production was. Right, but this is how you use the tool. You say, go back to somebody that's got to have some sort of insight into what we're going to be doing at this new plant, right? And ask them, what do you think the monthly volume is? And they're going to say, oh, couldn't possibly say, you know, we won't be online for another year, and we're not even selling to that market yet. And you say, well, pick you're the interviewer, pick a number. You know, like, well, do you think it'll be at least 3,000? Well, what if, I'm making up more to the story, but what if their response is 3,000? Are you nuts? You mean a month? No way. Come on, we're talking, we'd be lucky to be doing 1,000 a month, whatever this is, right? But I can't tell you exactly. I can't, you don't have to. If your expert is confident, there's no way it would peak out at like 1,000 a month at the absolute most. We don't need an exact number because we know where we would want to be. 1,000 a month is right here, right? If we want to be in Charlotte, we've got our answer. Thanks. You know, don't need any more. Or if you and ask that question, we think it'll be at least 3,000, and they're like, wake up! Are you kidding? It's going to be 10,000 a month at minimum, and I can't tell you. It might even be more than that. Whoa, 10,000 a month. I don't need at this point that we're just picking the city. I'm going to have questions later, but. I don't need to know anymore. I know where we need to locate, right? Because 10,000 a month is off the graph here. And clearly we'd need to be in Boston because that's always forever going to be the lowest line at that point. The high rent is worth it at that point, at that level, and we've answered the question. So really what this graph was it is a way to figure out what are essentially zones. Apparently, you'd want to be in Charlotte for low levels of production because the rent is cheap, basically, right? Charlotte would be preferred. It doesn't have very good variable costs, but it would still, since you're not producing much, then beyond a certain point, it's true, Omaha would be better. And yeah, it's basically this zone right in here. But it wouldn't be better forever because if production is high enough, we can clearly see that there is an argument for Boston. The only thing that we wish we knew, to be a little bit more specific, is where one stops and the other one starts. And there's a very important term for that. These points here where you change your mind, and you're going along this and this, oh, wait a minute, somebody else takes over, that is known as a point of indifference. There's 2 points of indifference here. One here, one here. They are where 2 different cities cross, and be careful, not every place that 2 lines cross is a point of indifference. Do you see that? Like where Boston and Charlotte cross right there, that's just, we don't care about that. It's just this one and that one. Well, I kind of wish I knew what that was where we change our mind from Charlotte to Omaha. The way to find it's super simple, and it has to do with the name. At the point that you change your mind is the one point that Charlotte and Omaha are they tie. They would be the exact same cost. You know, I'm pointing to it on a graph, which means you'd be indifferent if you happen to be producing at that level. You would not care, one or the other. And that's how we track it down. The only thing that we need to do to finish out this scenario is actually track down that exact amount. But why don't we, since I had a whole other page for that over here, why don't we just put a bookmark in it here and finish it up on Thursday? Thanks.